Okay, so given a set of n data points, and suppose that we have one segment where the variance is, say, 1, and in another segment the variance is equal to 2. And at some time point t, this change actually occurs. Change detection is interested in detecting this particular time point. And this has applications in various fields: financial, biomedical, audio, and in particular we consider accelerometer data. Now, right now in this work, what we do is we compare the univariate Markov Bayesian change detection algorithms against multivariate or multisensor Bayesian change detection algorithms, and we try to see why this occurs, or try to understand why this has occurred. Now, suppose we have n data points, and we're interested in estimating a vector of transition times, shown here by tau subscript k, where k is the number of transition times, and each element within the vector is an estimate of the change point location. Now, also, we have another vector of variances. That is, for each segment, we have a variance which is assigned to that particular segment. Now, there are a number of ways of estimating the target parameters of interest, which are k, tau subscript k, and the vector of the variances. One is using statistical significance tests, such as the generalized likelihood ratio test. Other approaches include dynamic programming. However, all those approaches are inference methods, and they do not enable you to do prediction, which Bayesian approaches enable you to do. So Bayesian both infers and gives you also the ability to predict. And how we infer the parameters, the target parameters of interest, we have to form what's known as the posterior distribution. Now, the posterior effectively says, okay, suppose we have our parameters. So suppose we have our data, or given our data, what is the best set of parameters which explains that data? And it's actually constructed of two particular terms, which is one is the likelihood, the evidence for these parameters, and our prior. So the likelihood is given by the first term in this line here, and the prior is given by the second term here. Now, the prior is effectively our belief in where we feel these parameters are. So, for example, we might think that there's 10 change points. So we include a prior which has, say, for example, an expectation at 10. So the probability of selecting 10 change points as our prior knowledge is higher than, say, for example, selecting 2 change points. Now, the likelihood, on the other hand, says, okay, suppose we have these parameters, we're given set of parameters, how well do they best explain this data? And the combination of these two of them gives us the posterior, which includes both the information of the likelihood and the prior. Now, in order to evaluate this, so the posterior distribution is a probability distribution. So there's a particular set of parameters where the probability distribution is maximal. And so how to evaluate that is a bit tricky. So some distributions, it's not tractable, there's no closed form solution. And so what we're resorted to is to draw samples from this distribution. Now, in particular, if you have distributions where it's not easy to draw samples from, you use what's known as Markov chain Monte Carlo algorithms. And in particular, we use a variation of the Metropolis-Hastings algorithm has been proposed or has been utilized. Now, the multivariate extension of the Markov chain Monte Carlo variance change detection algorithm first considers a matrix of data points where the rows correspond to the number of sensors, and in this case we have C sensors, and N corresponds to the columns correspond to the number of data points. And in order to understand why the multivariate approach improves upon the single sensor approach, or this univariate approach, what we do is we have to we estimate the covariance, but what we do is we assume for each segment the variance for each sensor is the same. So we have a common variance assumption. So our covariance is effectively a product of a single variance multiplied by the identity matrix, which is of dimension C by C, so the number of sensors. And as before, the target parameters of interest are k, tau subscript k, which again is a vector of dimension k, or length k, sorry, and a matrix, not a vector, of variances. Or in this case, the covariance. So we have k plus 1 of these covariances, which becomes a k plus 1c matrix. And the problem is the same as before. However, and the derivation of the posterior is about as similar, but there's a bit of a difference. But it's not a huge problem to evaluate this. Now, in order to see why the multisensory approach works better, we have to first consider the reasons for why we should be able to detect the change. That is, we want there to be a so suppose we look at just the upper panel, sensor 1, and we look at the first segment, shown here by a sigma squared subscript 1, 1. So the variance of the first sensor in the first segment, and the variance in the first sensor in the second segment. In order to have a difference, we need to be able to accurately estimate the variances within the given segments. Now, in general, in statistics, the more data points that you have, the more accurately you can estimate a statistical parameter, and in this case, we want to estimate the variance. So for example, if we only have 2 data points, our estimate for the variance will be extremely poor. So we confidently say that if we obtain a value, that's actually accurate. However, if we have 1,000 data points, for example, we can confidently say that this is a reasonably accurate estimate. And obviously you can mathematically show this, or statistically show this, excuse me. Now, by using the common variance assumption, what happens is that we assume that the variance for across the sensors for the same segment is the same. And actually the effect of that is to basically concatenate for example, so if we take the first sensor, first segment, we concatenate the second sensor, first segment, on the end of the first sensor's first segment. So we now effectively have more data points. So we can more accurately, estimate the variance for a particular segment. And if we can more accurately estimate a particular segment, we can actually differentiate between the two, and we can show this theoretically. So that's the intuition behind it. Obviously, assuming that the variances are approximately equal across the sensors. These are the results. So the upper panel shows the true positives, the middle panel shows the false positives, and the lower panel shows the error in the change point location estimate. So that's just if we estimate the change point, how close it is to the true value. These are synthetic data, so we've generated synthetic realizations. The blue is the the multivariate algorithm. The single sensor is shown by the orange or yellow, and the red is the average of the sensors fed into the univariate algorithm. And you can see the true positives are significantly higher for the multivariate approach. And the number of false positives is approximately equal to the average of the sensor values. And again, for the error in the change point location estimate, again, there's an improvement over both the single sensor and the sensor averaged approach. Now, the accelerometer data we analyze, we obtain from the UCI data repository, and it consists of a subject brushing their teeth with an accelerometer strapped to their wrist. And here we have a particular realization, and you can see that after high-pass filtering, or first differencing, which is effectively high-pass filtering, we have distinct segments where all three axes of the accelerometer approximately have the same variation in activity. So we have a low variance region, high variance region, low variance, high variance, etc. And the results are as follows. So the multi-sensor approach has a higher number of true positives, lower false positives, number of false positives with respect to the other methods. And so finally, in this work, we understood the reasons for why the multivariate or multi-sensor algorithm outperformed the univariate approach by using this common variance assumption. So we can actually kind of analyze why this approach worked. And the primary reason is because of the concatenation of the data for all the sensors for any given segment. Now, the ideas behind this work have actually led to another work which we've actually recently started working on, which is to say, okay, can we combine segments which have the same essentially parameter or same variance so that we have more data points, so that we can differentiate between the two, between any adjacent segment. So for example, if the variance in this segment is approximately equal to the variance in this, can we label these and combine these using, obviously within the Markov chain Monte Carlo framework, in order to actually iteratively find a solution. And so with that, I end my presentation.